Have you ever wondered why many solar panels are cut in half? Today, let's dive into it together. First, let's start with a simple experiment. Here, we have two solar modules. One is a traditional full-cell module, and the other is a popular half-cut cell. By simulating partial shading conditions, we can clearly see that the half-cut cell panel on the left produces a higher output power compared to the full-cell panel on the right. Now let's analyze why this happens. Traditional full-cell solar modules are like strings of Christmas lights. The entire system's output depends heavily on its weakest cell. If just one cell is shaded or performs poorly, the output of the whole panel significantly drops. In contrast, half-cell modules divide the solar cells into two halves and connect them in parallel. This way, even if part of the panel is shaded, the other region can continue operating. It's important to note that these two halves aren't entirely independent, a detail I'll explain later in this video. Another advantage of half-cut cells is that the series parallel wiring reduces the working current per cell by half. This significantly decreases the internal resistance losses of the module. In fact, resistance losses drop to just a quarter of traditional panels. Moreover, lower resistance losses reduce the risk of hotspot effects within the solar modules. Hotspots typically occur due to localized shading or cell damage, causing areas to overheat and potentially damage the module. The half-cut cell design mitigates this risk by reducing current and heat buildup, thus improving the durability and reliability of the module. What's even better is that this optimized design doesn't significantly increase manufacturing costs, making half-cut technology an economically efficient way to enhance solar panel performance. Consequently, half-cut cell modules have become mainstream, now making up over 95% of the market. You might wonder, if cutting cells in half is so beneficial, why not cut them into 3 or more pieces? Actually, cutting cells into two halves is ideal because it allows the shared use of a central busbar and bypass diode, creating the most cost-effective structure. One important practical consideration: the two halves of a half-cut module aren't completely independent since they share one bypass diode. If one half of the panel is shaded, the central inverter might push the entire string to run at high current, activating the bypass diode. As a result, the entire panel gets bypassed, making it similar to traditional full-cell modules under shading. So, how can we fully utilize the advantages of half-cut modules? First, consider using microinverters or solar optimizers, enabling each panel to perform at its optimal level. Secondly, choose between portrait or landscape installation based on shading conditions, ensuring shading only impacts half of the panel. Thanks for watching. See you in the next video.